Hello everyone. In this video, we are going to show you the details how a high-performance amplifier is designed and built. This amplifier works as a high-performance headphone amplifier as well as a line stage amplifier. Therefore, you can use it directly to drive any headphone or audio power amplifier. Okay, let us dive into this audio amplifier project now. This is the schematic of the amplifier. As a matter of fact, this amplifier has two versions. This schematic is the first version in that 4-junction field effect transistors, or simply called JFET, are used in the input stage. They are transistors Q3 to Q6, which are enclosed by a red color rectangle. Several components with values shown in red color are associated with this version. The second version employs 4 bipolar junction transistors, or simply called BJT, for Q3 to Q6. Again, there are several components with values shown in red color associated with this second version. Now, we take a look of this amplifier design closely. Let us start with the first version, which employs JFET. Generally speaking, the amplifier can be divided into 3 parts. The first part is the input stage. The second is the voltage amplifying stage, or simply called VAS. The third part is the output stage. The fourth part, which is not shown here, is the DC servo. We will discuss the DC servo later. This is a simplified schematic that emphasizes how the input stage works. The second stage, which is the voltage amplifying stage, and the output stage are represented by 2 block diagrams. They will be discussed shortly. It can be seen that the input stage consists of 2 complementary cascode differential amplifiers, which produce low distortion and broad bandwidth. The first differential amplifier is formed by transistor Q1 to Q4. Transistors Q11 and Q12 form a current source that produces a tail current of 2 mA for the first differential amplifier. The second differential amplifier is formed by transistors Q5 to Q8. Transistors Q9 and Q10 form a current source producing a tail current of 2 mA for the second differential amplifier. The input stage can be viewed as a difference amplifier that has 2 inputs. The first input comes from the input source, for example from a DC player. The second input comes from the feedback signal of the output. The input stage compares the 2 inputs and amplifies the difference between them. Then it generates 2 outputs to point A and B. This diagram shows the input waveform and 2 output waveforms from the input stage. They are aligning on the same time axis for comparison. Please also note that the DC potentials at point A and B are positive 22 volts and negative 22 volts respectively, which are carrying over from the input stage. Since the input stage and the second stage are directly coupled, these 2 DC potentials are crucial in determining the desired DC quiescent current for the second stage. Also note that the 2 outputs are in phase, and fluctuating at positive 22 volts and negative 22 volts, respectively. However, the 2 outputs are 180 degrees out of phase with respect to the input waveform. This is a simplified schematic that emphasizes the second stage. The output stage is represented by a block diagram, which will be discussed shortly. The second stage is the voltage amplifying stage that produces a high voltage gain for the entire amplifier. In this voltage amplifying stage, it contains 2 complementary cascode amplifiers with their output connected together. The first cascode amplifier is formed by transistors Q13 and Q14. The second cascode amplifier is formed by transistors Q15 and Q16. In the cascode amplifier formed by transistors Q13 and Q14, the output is produced from the collector of transistor Q14. And the load seen by transistor Q14 is the collector of transistor Q15. Similarly, the impedance from the collector of transistor Q14 is the load for transistor Q15. Since impedance from the collector of a BJT transistor is high, the cascode amplifier produces a very high voltage gain. On the other hand, there is a resistor network formed by resistors R20, R21, and R22. The purpose of this resistor network is setting up a desired DC potential at the base of transistor Q14 and Q15. In this schematic, the DC potentials are 12.3 volts and negative 12.3 volts as shown in the schematic. Here we have two output stage configurations. The one in the right is a popular emitter-follower triple. The one in the left is the diamond buffer amplifier used in this headphone amplifier. Both configurations work as a buffer amplifier to be placed after the second stage. The output stage drives a load directly. The properties of buffer amplifier include 1. Unity voltage gain, 2. High input impedance, 3. Low output impedance, 4. Broad bandwidth, and 5. Sufficient output current to a load. In the emitter-follower triple, there is a VBE multiplier that creates a DC voltage spread, so as to set up the DC bias current for the three pairs of emitter followers. However, the VBE multiplier is physically part of the amplifier's second stage. In other words, the DC quiescent condition of the output stage is controlled by the second stage. Nevertheless, when the entire amplifier is designed and operated properly, the amplifier should be fine. On the other hand, the diamond buffer amplifier is standalone and independent from the second stage. The DC bias current is set internally by the buffer amplifier itself. From this schematic, there are two current sources. They are operating in current mirror configuration. The current source on the top is formed by transistors Q17 and Q18. The other current source on the bottom is formed by transistors Q19 and Q20. Since these two current sources are connected through resistor R24, they are running at the same current of 3.5 mA. As the current source on the top is operating in current mirror configuration, a same amount of 3.5 mA flows into emitter follower Q21. Similarly, the current source on the bottom also operates in current mirror configuration. It produces 3.5 mA flowing into the emitter follower Q22. After the DC bias currents are set up in Q21 and Q22, the total sum of the following voltages creates a DC voltage spread. The voltages are 1. VBE of Q21, 2. VBE of Q22, 3. The DC voltage potential across resistors are 27, and 4. The DC voltage potential across resistors are 28. This DC voltage spread eventually set up the DC bias currents for the next two emitter followers formed by transistors Q23 to Q26. Therefore, all these DC bias currents in the diamond buffer amplifier are independent from the second stage. Since the DC bias currents are set up internally inside the diamond buffer amplifier itself, the DC stability of the output stage is almost unaffected by the second stage. Therefore, the diamond buffer amplifier output stage has an improved DC stability over an emitter-follower triple output stage. If we want to find an expression for the voltage gain of the headphone amplifier, we simplify the schematic as shown here. It is identical to an amplifier formed by an op-amp in a non-inverted configuration. Therefore, the voltage gain is determined by two resistors, R3 and R4. Given with the values as shown below, we can easily calculate the voltage gain. It is given as 7.7, which is consistent to actual measurement from this amplifier. If we want to change the voltage gain to other value, say a gain of 9, we can simply change the resistor R4. For example, if we choose 15K for R4, the voltage gain becomes 9.3, which is close enough. There are several so-called compensation capacitors used to stabilize the amplifier at high frequency. They are capacitors C1 to C5. Capacitor C1 is the one directly mounted on the feedback resistor R4. For this headphone amplifier, the voltage gain is set to 7.7. All compensation capacitors are so chosen that the amplifier has a very broad bandwidth, and there is no sign of oscillation appearing in the output. For this amplifier, C1 is optimized at 68 picofarad. However, if the voltage gain is changed to value different from the original 7.7, a 68 picofarad capacitor may still work for C1. But it would be better to verify if it is still the best choice. It is also true for the other compensation capacitors C2 to C5. Nevertheless, if the voltage gain is not too far from the original 7.7, we may not need to worry too much about the stability of the amplifier. Even if we decide not to change the capacitors for C1 to C5. Here are some outputs from the amplifier in response to a square wave input signal. 3 input frequencies are tested. They are 1 kHz, 10 kHz, and 100 kHz. When the compensation capacitors are chosen correctly, the square waveforms are very nice. For frequency 1 kHz and 10 kHz, the shapes of the square waves are very well preserved. When the amplifier's high-frequency response is overcompensated, so as to enhance the stability, the bandwidth of the amplifier is reduced. As a result, the 10 kHz square waveform has a severely rounded rising edge and falling edge. For the frequency 100 kHz, the waveform does not even look like a square wave anymore. Even though the amplifier is very stable, the bandwidth is unnecessarily reduced. When an amplifier is undercompensated, it may seem to have a very broad bandwidth. However, the outputs contain a very high frequency oscillation superimposed to the square wave. When we see this kind of very high frequency oscillation superimposed to the output waveform, there are 2 things we have to be aware of. First, the audio produced from the amplifier may sound unnatural. Second, the amplifier is prone to be unstable. We have to remind ourselves that in amplifier design, the top design goal is always to avoid instability from occurring to an amplifier. For comparison purpose, we gather together 3 10 kHz square wave responses. It is clear that when correct compensation is used, the amplifier produces very nice square waveform. These 3 waveforms may suggest to us that there is a way to determine the correct values for the compensation capacitors. First, we start with using high-value compensation capacitors, so that the amplifier is overcompensated. Therefore, the amplifier produces output square waveforms with severely rounded rising edge and falling edge. Then we reduce the capacitances until oscillations begin. At this point, stop and increase the capacitances slightly until all oscillations disappear. Now the values of these compensation capacitors represent the correct compensation to be used by the amplifier. We have just discussed the first 3 parts of the amplifier. They are namely the input stage, the second stage voltage amplifier, and the output stage diamond buffer amplifier. Now let us take a look of the final part. A DC servo is a circuit that reduces the amplifier's output DC offset to nearly ground level. General speaking, if a headphone amplifier is well designed and well-matched transistors are used, the output DC offset voltage is less than 100 mV. If it is just used as a headphone amplifier, 100 mV is usually acceptable, but of course the lower the better. Since this amplifier serves dual purposes. A headphone amplifier as well as a line stage amplifier. Output DC offset is best to be kept below 10 mV. In the PCB, red rectangles represent the DC servo. However, let us skip the discussion of the operation of DC servo this time. Otherwise, this video will be too long. In the future, we can make a separate video for it. For the moment, if you are interested, you can check out the reference book given in the description section on this video below. The reference book fully covers the operating principle of a DC servo and gives various application examples. Since this amplifier can be operated as either a headphone amplifier or a line stage amplifier, therefore, there must a switch to set the operation between them. The headphone socket as shown in the photo is the required switch. The electrical symbol for the headphone socket is given here. There is a switch for contact between A and B. This is for the right channel. There is another switch between contact C and D. And this is for the left channel. Contact E is the ground. As a matter of fact, the headphone socket operates like a double-pole double-throw switch. This is a block diagram showing how the headphone socket is connected to the headphone amplifier, without a headphone jack inserted to the socket. Just like what this diagram shows. This amplifier becomes a line state amplifier. The right channel's output goes out to contact A, then to contact B, through the switch. Similarly for the left channel. In this simplified diagram, it illustrates that when no headphone jack is inserted to the socket, this amplifier operates as line stage amplifier. This line stage amplifier can drive any audio power amplifiers that take unbalanced signals. When a headphone jack is inserted to the socket, the two contacts break open. Therefore, the output signals all go to the headphone. Contacts B and C receive no signal from the amplifier's output. Therefore, the amplifier is now operating as headphone amplifier. This headphone amplifier offers excellent measured and sound performance. The distortion is less than 0.005% for output power up to 1.5 watts. This amplifier can deliver up to 2 watts except with a slightly higher distortion. This output power should be sufficient to drive most headphones available in the market today. Due to the length of the video, it is now the end of part 1. The PCB assemble work and constructing an entire unit of the headphone amplifier will be continued in part 2. I will see you there. If you are not subscribed to the channel yet, and are enjoying these kinds of videos, then please think about clicking the subscriber button below, so I can continue to make these videos for you. I will see you in the next one.